Hi everyone, my name is Stefan Mabry and I am a PhD student in computer science at the University of North Dakota. My background spans nearly 2 decades working at the intersection of healthcare, data, and technology, from leading projects at Epic to consulting with health systems on quality improvement and digital transformation initiatives. This project is focused on explainable artificial intelligence, or XAI, and how we can use it to understand the role of social determinants of health in predicting clinical diagnoses. As we push more AI into healthcare workflows, explainability becomes a non-negotiable factor. Clinicians need to trust and understand what models are doing, especially when social context is involved. Originally, I set out to predict total costs of care using SDOH data, but after extensive analysis, I found that shifting the model's target to clinical diagnoses opened up a clearer signal and stronger insights, all while keeping the explainability at the center of the work. And I'll chat more about that as we get to the challenges and preliminary results section. So let's get the focus into heart here. So the heart of the research is this: can we use AI to reveal how social factors like income, education, or access to care actually influence the diagnoses that patients receive? So from the formal research question, that we're driving with is, given a model trained to predict clinical diagnoses using social determinants of health, can explainable AI methods like SHAP help us understand which specific social factors contribute to each diagnosis prediction? That's the lens we're working from, and the end goal isn't just predictive performance, but actual insight. I want to be able to say, here's why this model flagged asthma or diabetes, and here's how social risk factors contributed to that call. In other words, I'm not just about building a powerful model; it's about where we can make logic visible, and this is where explainability, with AI comes in. So I'm using SHAP to unpack the model's behavior and surface the top contributions to each condition. And that's going to help us try to uncover why the diagnosis is being predicted. I don't really think it's true explainability, but I'll get to that in a second. So I know that most of you don't have a clinical background, so I'll explain a few terms. So a diagnosis is a clinical determination about what condition a patient is experiencing, like asthma, diabetes, or depression. Clinicians choose from over 68,000 standardized ICD-10 codes to document the conditions. That's a newer thing, but newer as in like 15 years. But anyway, so some of the diagnoses are actually pretty specific. My personal favorite is the W56.22XA, which is struck by orca initial encounter. So apparently somebody was hit by an orca at some point, and that's why we had to have a code for it. So SDOH, or social determinants of health, that refers to non-medical factors that shape health outcomes, like income level, housing stability, access to nutritious food, reliable transportation and education. There's also like what factors are in your home, like lead or mold, what the abuse situation looks like, both physical and sexual abuse. So it really factors in like a wide variety of conditions that might influence a diagnosis. And then, XAI, or explainable AI, I don't actually like anyone else's definition of explainable AI, and arguably true explainable AI, at least at the neural network models, it doesn't exist today. They're all post hoc methods instead of intrinsic to the model. But that said, my definition of explainable AI is it's the science and practice of designing AI systems that provide human interpretable justifications for their outputs, enabling trust, accountability, and improved decision making while maintaining predictive performance. So we'll move on. So this slide represents the full life cycle of my project. So as you can see, I've completed 3 major steps. The first one is data exploration. I've deeply explored the MEPS data set, which I'll talk about in a minute, and I've investigated over about 260 variables including those related to both clinical and SDOH domains. This included analyzing distributions, checking correlations, and identifying missing or ambiguous values. The original project was focused on total expenditure, but this data set only includes total expenditure for a single year, and the prediction of total expenditure was not possible from any variable or collection of variables within the data set, which is why I had to pivot away from it to diagnoses. And then focusing on, of course, social determinants of health. That was always part of the project. There's step 2, which is the feature engineering. So I standardized, encoded, and cleaned up all the SDOH related features, and I'll show you that code momentarily. So, and I also recorded the diagnosis labels. I fixed those as well. I also converted all the non-yes values to 0, and I'll talk about that also later in this video. But I'm making them a binary choice between yes, I have this condition, or no, I don't. This is important because if a patient goes to an appointment for diabetes and the clinician never looks at the patient having cancer, then the value is recorded as a -1 or not applicable because it was never evaluated, and the physician can't say, does the patient not have cancer or not? But in those cases, because they don't have any symptoms, they don't have cancer. So that's actually a no. So the actual data set for the diagnoses is mostly composed of these -1 values, and so I converted them to no's. Then step 3 was the coding and training of the models. So I trained a separate neural network model for each diagnosis condition, allowing me to account for label independence and handle class imbalance better. This approach yielded higher accuracies and F1 scores across a variety of conditions. So far, things are tracking well. Trying to predict a particular diagnosis yielded poor results when I tried to merge all of the diagnoses together. And then some next steps. So, they include fine-tuning these models and building a lightweight ensemble strategy to expand the neural network models to other machine learning methods, because I want to be able to compare them, compare explainability across those models, or maybe even use all 3 models to compare explainability. And I'll tinker with that as the project goes on. Then I'll shift into explainability itself using SHAP values to analyze the most influential SDOH factors for each diagnosis. And then that's steps 5 and 6. And then from there, it's just a matter of drafting the final paper and presentation, which I'll complete over the next 2 weeks probably. And then overall, I'm on track with having the project completed and recorded, probably in about 2.5 weeks or so, which is, before the deadline. So let's talk about the data set I'm using. So I'm using the MEPS, or the Medical Expenditure Panel Survey. So MEPS is a large-scale, nationally representative data set maintained by the AHRQ. It's designed specifically for analyzing healthcare utilization, costs, and insurance trends over the United States, and it's widely used in health economics and policy research. From a research standpoint, it's a gold mine if you're looking to understand how healthcare happens in the real world. Only 1 year recorded SDOH data, which is 2021, and so that's the year that I'm working from. One of the biggest strengths of the MEPS, and why I chose it, is how deeply it captures those social determinants of health in that 2021 year, and it's 20-something features or more that are all SDOH related. I'll show you those in a second. But they include things like income, education level, employment, housing stability, access to care, all those upstream social factors that can shape downstream clinical outcomes. But MEPS data isn't perfect. It uses a rotating panel structure, which means that it only follows patients for about 2 years. And then, that's a short window that limits the ability to do any type of long-term or chronic disease modeling. For this project, it means that I can't model lifetime costs of care, which was my original goal, but it still provides plenty of signal in predicting clinical diagnoses, which is where I pivoted. And I've linked to the data set here for anybody who's curious to explore it. It's open, well documented, and it's surprisingly usable. Speaking of the data, this is what an actual record looks like. It looks kind of confusing and intimidating, but it's a fixed width text file. There's no commas, no headers, just raw positional data. Each column is defined by a character placement, so the schema has to be read in separately using column specs. There's a file that they provide, but I wrote my own. It's kind of messy, but the data is highly structured, and with the right parser, it can turn into rich data set. And there's over 1,400 variables per person in here. So covering everything from income to insurance coverage to medical diagnosis, events, military activity, things that are self-reported. So that's, I guess, part of the signal degradation is that these conditions are all self-reported. So before I do anything with this data, though, I have to, first wrangle it into something usable, which is where the pre-processing steps come in. So this is the processing process that I have in place. So, how do we actually make sense of all the wall of numbers and dashes from the previous slide? Well, this is a sample from the MEPS code book. This is the left section here, the blue. And it essentially, it's a key that tells us how to decode the fixed width file. And then also, if you click on these, you'll see what the data set looks like what that element looks like and what the values are. So you can interpret then a 0 is this value, or 1 is, yes. But, each row represents a single variable. The name, which is their name for it, which is a code and not necessarily human readable. There's also the start, which is what position, which character is the first character of that in the positional file, and then there's the end, which is the end character, and then a description of a human readable description of what this thing is actually meaning. So as I said, military full-time active duty, and these three shall have a different evaluation. And I don't understand all of them, obviously. I just understand the clinical ones. So, for example, if you take ADHD, ADDX, that's a variable for whether a child has aged specifically between 5 and 17 has ever been diagnosed with ADHD, and then you'll find that between the characters of 445 and 447 for each record. There's over 1,400 of these data positions in data columns. So everything in MEPS works like this. No column headers, just position-based mapping. So before we do any machine learning or even basic cleaning, you have to load the schema and then line it up with the file structure to extract the real values. So I translated the code book into a positional tuple ranges, which is this middle section here. And this is just a snippet, or in fact the same rows, showing us how the CSV that I created operates. So, because Python begins the first position at the 0 character, and then it moves forward from that position, I had to add 1 to the range, stepping back the tuple's position for evaluation. And then I turned the names of the columns so that I can reference them more easily into the basic human. So I basically took the description and I turned that into a number, and then that becomes the column names themselves, and then I can just map them back and forth when I'm doing my analysis. So using those names, I then load everything into memory. We're only dealing with about 28,000 records or so. So this is okay. Normally it would not necessarily be okay because it might run out of memory limits. 1,400 data points over 28,000 records is actually a lot. But my machine can handle it, so I ran with it. It'd be a lot more efficient if I just loaded the data components that I want, but I started there, and then tracking all the ranges in Python was a chore. So now I'm loading up everything, and then I drop all the stuff I don't want, and this lets me stay flexible and explore the data more easily. And so that's what this code section over here is. So this is the loading code, and then this is how I pull the column names and the specs out from this sheet here, and then I dump it into the data, and that takes a couple minutes. And then I process the data So I clean up the diagnosis codes, and then if the patient visits appointments for diabetes, and they've never been evaluated for cancer, then that's an NA field. So I switch that over to a no, and that happens down here. This clean diagnosis labels. So each step of this is just processing the data into something that's usable. So exploring the data a little bit. What is the data actually showing us? So the first chart here is a correlation matrix. It's on the left. This shows how the social determinants of health variables, and you can see what I called them over here. These are actually like my better names, not the ones I'm using in my code. But for example, do you attend church is one of the questions. Do you get help from the community? Do you get moderate exercise every day? And it covers the whole gamut of social conditions. And I find this chart actually kind of depressing. And I'm going to tell you why in a second. So some of these relationships are exactly what you'd expect. It's like if somebody struggles with food access, they probably also struggle with finding affordable housing, transportation, or utilities. But what really stands out is the density of correlation. These factors don't just connect, they kind of pile on. So if your life is hard in one category, chances are they're hard in several other categories as well. This is like the life stressors stacking. It's like this, for example, this box right here of red. It's highly correlated that if you have problems cooking, you also have problems with lead, and you've got problems with mold and pests. It's just really depressing. The top right chart over here, now we got a raw cost distributions. So this is like the total expenditure of healthcare over the course of the year, and it's a bit ugly. It's hugely skewed, and with a small number of people racking up massive costs, and then a vast majority clustered towards the lower end. I did a log transform to normalize the scale a bit, but as you can see on the far right, it didn't really help very much. And then every model I tried using, the SDOH data or 260 other data columns trying to figure out what might correlate to this. Every single one of them had a negative R-squared value, which means that the model performed worse than simply guessing the mean. So in other words, it's completely useless. So that's a big reason why I pivoted towards predicting diagnosis instead. So then lastly, this bottom right-hand chart, I'm not expecting you to read this. The point is not to read this chart. But it's a completeness check. So this is actually me showing you that every single data element is clean and fully populated. So there's no imputation needed, although the government did do some imputed fields. But many of the fields have already been pre-processed by the government, which is rare, but we're not wasting a lot of time patching the holes or trying to make some of the hard decisions. They've already had, more experienced data scientists patching holes for us. So let's focus on the modeling and the explainability a little bit more. So the overall algorithm, so step one, I load the data, and so we saw those functions on the previous slide. And step two, and then preparing, then cleaning the data, so you saw those functions also on the previous slide, or 2 slides back. Step three then is identify in one hot encode the category values, but this step doesn't actually do anything since the data is already encoded, and we saw in our example, it's here for me to reuse the code with other data sets later, so I don't have to rewrite it. And then, once we have everything prepared, I run the model for each of the 20 diagnoses that I'm evaluating. And so, this is my first success with the project. I had a lot of iterations before this that all failed. Not code-wise, the code was fine, but the models themselves didn't produce anything usable. So what am I doing that's working? So let me walk you through the algorithm here. So to start, the core design loop, I'm building one neural network per diagnosis field, and I'm doing them all with the same random generated state to start with. And so that's because each diagnosis is treated as its own binary classification problem. It's does the patient have this condition or not? There's no meaningful relationship between the different diagnoses in the data set that would justify a multi-class or multi-label setup. I tried doing them all together, and my results were absolutely terrible. Inside this loop, then, the first thing I do is I handle class imbalance because I train each diagnosis model independently. The class distribution can vary widely per condition. Some diagnoses are very common, and others are extremely rare. So, and you'll see those numbers in the next chart, the next slide. But for those rare diagnoses, the model might otherwise default to always predicting no because that's statistically safer. So I use random oversampling with each diagnosis training set to rebalance the positives and negatives, so that giving the model enough signal to actually learn what separates a positive case from a negative one. Next, I do the standard train test split of 80-20 using the train test split function, and then I apply feature scaling, which uses the standard scaler. Now, in most cases, scaling helps neural networks converge faster and better, but in this case, it's a little bit more nuanced. The diagnosis is binary, because I made it that way, but it was, for the most part, binary before. And then, many of the SDOH features are encoded categories, not continuous values. So in theory, scaling might not be strictly necessary here, but since some features are numeric, like income or age, as I move things around, neural networks are sensitive to those input scales. So I kept the scaler in place for consistency and performance. For use, if I use those other condition fields like I had initially. So then I build a pretty standard feed-forward neural network using Keras, 2 hidden layers with ReLU, and then a sigmoid output for the binary classification, and then binary cross entropy as the loss function. To avoid overfitting, I use early stopping and restore the best model weights. And then after training, I generate the predictions. I set the threshold to 0.5, and then I compare them to the true labels using accuracy, precision recall, and F1 score. And then the loop repeats for all the diagnoses in the list, and I collect the results into a data frame for analysis. So then, here's the model results. So these are the preliminary results for each model that it was created. 1 model per diagnosis. Each row here represents a separate neural network trained to predict whether or not a patient has a specific diagnosis using the social determinants features as inputs. It took a bit of time and a fair amount of trial and error to get here. There was a lot of data exploration, cleaning, filtering, encoding, and testing. But now I've got a solid foundation of trained models, and each of these is ready for the next phase, which is ensemble, getting an ensemble model set for each one of these instead of just the neural network, and then use explainability to try to figure out why it says what it says with any given prediction. So the accuracy and F1 scores show the models are learning something, but the results vary. So rare diagnoses like bladder cancer perform well after oversampling, likely because the signal is clear when present. In contrast, more common diagnoses or conditions like high cholesterol or arthritis perform worse, possibly because they're spread across a diverse population without strong social patterns. Some diagnoses might actually lead to worse SDOH outcomes. So for example, like ADHD, it might make it harder to hold a job, and then therefore causing some of the problems that you might see with an SDOH questionnaire. And then others like mold exposure or poor housing questions those situations might lead directly to having an illness. And then some diseases like arthritis may just largely be independent of social factors altogether. So these are all plausible explanations. But it's why we need to have the explainable AI methodologies alongside predictions. And that's what the value is in healthcare, to have true explainable AI, and not just the kind of band-aid fixing of what we do in the modern era. But it can help us, dig into why, the model made a decision and what the social features contribute to that outcome. Rather than stop here, I'm planning to expand this framework into an ensemble strategy, combining neural networks with other model types like random forests and gradient boosting. And that way, I can compare the explanations generated across different modeling approaches and assess how consistent or reliable the feature attributions are. I want to be able to see if the models are consistently explained for the same disease with different random starting conditions as well. So, like, I'll run the same neural network with different random conditions to see if then the SHAP explanation is consistent across those models for the same disease. So each model I create will have a specific random seed value instead of a truly random starting seed, so that we can actually control and reproduce the results of explanation very clearly. I don't really care about the model itself. I care about the explanation aspect of it. So then, the goal, of course, then is then exploring the explanations given by the XAI methodology, in this case, SHAP. So the question becomes not just can the model make the prediction, but do different models explain the prediction in the same way? And that's where the XAI piece really kicks in. So now that we have those working models and solid performance across several clinical conditions, here's what's next. First, I'm going to expand beyond neural networks and build that ensemble method for each of the diagnoses. That includes decision trees, logic regression, XGBoost. The goal is to test whether different algorithms converge on the same predictive patterns, using SHAP. And then next, I'll apply SHAP to the top performing models to uncover which social determinants of health actually drive predictions, not just whether a model works, but why it works. And then from there, I'll compare the explanations across these models to see if they agree on which social features matter. If they don't, that tells me something important about the stability or fragility of our interpretability methods. And then finally, I'll pull all this together into a structured narrative, finalize the paper, generate visualizations, prepare a final presentation that highlights both the findings and the limitations using AI to interpret social drivers of health. So that's where I'm at. It's normally where I have, see if you got any questions. However, you can reach out to me on the internet. So my email address is above, and then you can also use the QR code to reach my LinkedIn page. And then, of course, if you're ever in Madison, Wisconsin, feel free to give me a visit and we can hang out. Thanks and have a great day.